Hello everybody. In today's video, we're going to talk about inverse relations and functions. Today we're going to learn how to define inverse functions, and then we're going to represent inverse functions as a table, graph, and an equation. Alright, so what is an inverse relation? In order to know what an inverse function is, we have to know what an inverse relation is. So what is an inverse relation? Let's look at this chart, right? So here we have a few values. We have when x is negative 2, y is 1. When x is negative 1, y is 4, right? We just kind of read it. Of course, the set of all x values is our domain, and the set of all y values is our range. So in an inverse relation, the domain and the range are flipped, right? So if we're finding the inverse relation of this initial chart, we're going to flip the x and y values, right? So you'll notice here, instead of it being y is 1, x is negative 2, now it's x is 1, y is negative 2, right? And so on and so forth. So an inverse relationship is the same as the original function with the x and y values flipped. All right, so now we're going to ask, is this inverse relation an inverse function, right? So it's one of those things where it's like all squares are rectangles, but not all rectangles are squares, right? All inverse functions are inverse relationships, but all inverse relationships are not necessarily functions. So this is just kind of asking, is it a function to begin with, right? So is the inverse relationship a function? Well, a function is a specific, when you say is it a function, you're actually asking a very specific question. And you're asking, does our function have, or does our relation, or however you want to call it, does our phrase have exactly one output for each input, right? And remember, output would be our y value, input would be our x. So in other words, does every x value have only one y value associated with it? So I've always thought of this as like a machine. This is arguably the greatest mathematical drawing ever. So I showed that, like, the input here, right? We put in a 3. It goes into our function of 2x plus 1, right? And then because it was a 3, we put it in where the x is, and we got 7. So it spit out a 7, right? So you'll notice that if we use 2x plus 1, if we put in a 3, the only answer we can get is 7, right? There's no other answer that works for this. This means that 2x plus 1 is a function, right? This is a rule that establishes a function. So that's kind of the idea behind this, right? If we have like a list of terms here, then every x value should only have one y, right? So let's go ahead and look up here, right? Okay, well, let's just take like x equals 1, y equals negative 2, right? But here we have when x equals 1, y equals 1. So in other words, when x equals 1, we don't know if y actually equals negative 2 or 1, right? Well, actually it equals both, right? But in terms of a function, that's not allowed to happen, right? So in this case, when x equals 1, y equals negative 2 and 1, which means this is an inverse relation, but it's not an inverse function, okay? And that's kind of what you're checking for, right? If you look at it on a graph, right? So let's go ahead and just real quick look at it on a graph, right? Anytime you see things that look like this on a graph, right, you can do what's known as the vertical line test, right? So if you imagine that my cursor is like a pencil, right, and we're going from side to side, there's going to be no problem here, right? But remember that your pencil, which is like establishing along your x values, right, here along your x-axis, remember that if it ever touches more than one y value, that means that that x value has more than one y, so it's not a function, right? So in other words, if we look at this function here would not pass the vertical line test, because as soon as you get past 0, all of these values have two numbers, right? So in other words, like here, if I was just looking at it, right, this looks like it's 5 comma 2.2, and then it would be 5 comma negative 2.2, right? So 5 can't be both of those in a function, right? So this wouldn't be a function. However, if we look at something like this, right, where you notice all we did is kind of rotate it, right? In this case, we have y equals x squared. If we do that for every x value and we go across, right, you'll notice that we're only ever going to get one y value. If you just pick a random x, let's say 1, right, well, where x is 1, y is 1, right? Where x is 3.17, y is 10.04, right? And so on and so forth. There's only ever one y for every x. Okay. So let's find the equation of an inverse function. And you'll notice here that I have this notation of it looks like f of negative 1 of x. This is the notation for inverse. So in other words, if we're finding the inverse of f of x, then this is what this would look like, okay? So if f of x equals x squared, find the inverse of f of x, is essentially what this question is asking. And remember, like we said over here, all you're doing is flipping the domain and range. In other words, you're flipping the x's and y's. So if I plug in the x where the y should be, and I plug in the y where the x should be, then I can solve for y, and that'll give me what the inverse function is. So if I have f of x equals x squared, if we write this in terms of y, we can say like y equals x squared, right? So if I switch this around, if I flip the x and y, I'm going to get x equals y squared. And then remember, we want to solve this back so that it says y equals something, right? So if I want to say y equals something, I'm going to have to take the square root of both sides, which means I have to take the positive and negative, right? And this is going to give us y equals positive and negative square root of x. So this here, y equals positive and negative the square root of x, is the inverse of x squared. And if you think about it, remember how I taught you that square roots and squares are kind of like inverses? I mean, it's not the best phrase for it, but essentially that's what they are. Well, this is kind of me proving that to you, right? It would be the same thing as if you multiplied something and then divided it, right? You'd have an inverse function. All right. So restrict the domain to make an inverse relation an inverse function. All right. So in other words, let's go ahead and go back to Desmos, right? Okay. So y equals x squared is this graph that I showed you here in the red, right? And then y equals plus or minus the square root of x is this, right? You have to do both because, yeah, we learned that neither of these go negative, right? Okay. So these are our two functions, right? You'll notice that in this case, y equals x squared, the inverse of y equals x squared is not a function, right? So what we can do is we can restrict the domain of our original function so that the inverse is a function, right? So in other words, if we restrict the y equals x squared to just x is greater than 0, so in other words, if we pretend like this half is gone, right? So let's take this and let's restrict it, right? So let's restrict it such that, like this, let's say x is greater than or equal to 0, right? So now all we have is this piece, right? Well, what that's going to do is when we restrict the function over here, the only piece we're going to have now is going to be this positive piece, right? The negative piece would drop off. Just like we got rid of the negative function up top, this will get rid of the negative function below as well. And now, this is actually really cool. If you remember from when you did reflections back in geometry, anytime you have inverse functions, they should reflect over the line y equals x. And this makes actually kind of a beautiful little graph here, right? Where we have the positive half of y equals x squared, and then we have y equals the positive square root of x, right? You'll notice that this is a function, right? These two things are functions. Neither this red line or this blue line are going to fail the vertical line test. These are going to pass in both situations. So we could restrict the domain to make this work, right? Now let's just see what happens if we restrict this the other way, right? So this is plus or minus, or this is greater than x, or greater than 0. So let's try less than 0, less than or equal to 0. Okay. So now let's just do the negative side. This also looks like they're inverses, right? Well, they are. And do these pass the vertical line test? Yes, they do. So we could restrict this. We could restrict this domain multiple ways, right? In order to make this actually an inverse function. But in order to make it an inverse function, we have to restrict the domain, right? Because as I said before, like this doesn't work, right? Because you'll see that this blue graph here now that's not going to be a function, right? So that's, if you ever need something to be a function, you can restrict the domain so that way you can turn it into a function. All right. So let's look at this. We're going to find the inverse of f of x equals x squared plus 8x plus 16. I'm going to go ahead and let you pause the video now. Go ahead and give it a shot. I'll give you a hint. It should look like when we found the when we were finding perfect squares before. Remember how we used perfect squares to solve quadratic functions? So let's see if you can get this. So go ahead and give it a shot, and if not, pause the video and I'll come back and we'll help you out. All right, so if we are finding the inverse of f of x, we're going to substitute in y for x. So everywhere we see an x, we're going to substitute in a y. Everywhere we had a y, we're going to substitute an x, and then we're going to solve for y, right? Okay, so let's go and do this. So what we would have, if we just wrote this out, is y equals x squared plus 8x plus 16. Okay, so let's flip this, right? So now we're going to have x equals y squared plus 8y plus 16. Okay, so now we're going to use trinomial factoring, right, which is a big term for basically saying what multiplies to make 16 that adds together to make 8. And that's going to be x plus 4 and x plus 4, right? Remember completing the square? That was kind of the hint I gave you earlier. So now we're going to have x equals, right? And this would be like y plus 4. I'll go and just write this out just to make sure that you understand what I'm saying. This is y plus 4 times y plus 4, right? And that's going to be the same as y plus 4 squared, right? Because it's the same, it's that times itself. Okay, so we have x equals y plus 4 squared. Well, how do we get rid of something squared? We take the square root of both sides, right? And remember, we have to take positive and negative because it's a even degree function, or it's an even degree root. So we'll have plus or minus x, or the square root of x, equals y plus 4. So how do we get y by itself? Well, subtract 4. And we're going to get y equals plus or minus the square root of x minus 4. Okay. Now, remember, if we remember from transformations, right, this is going to be the y equals plus or minus x graph that we just kind of looked at, right? But it's going to all be shifted down 4 units. Just if you're kind of figuring out what it would look like, right? Now, so if you're curious whether or not you'd have to restrict the domain in this case, well, yeah, of course you are, right? It's the same exact idea. We have x squared, right? And now we could restrict the domain any number of ways here as well, right? But ultimately, like, the easiest way to think through this is just to graph it and go, right? We can do this real quick. There's no reason why not. So let's do x squared plus 8x plus 16. All right, I'm going to get rid of all these other ones real quick. And then the other one would just be, it was the square root of x, minus 4. And then the other one was the negative square root of x minus 4. Cool. And all right, x squared plus 16x, or plus 8x plus 16. Okay, perfect. All right, so now I'm just gonna turn this one blue just so we can kind of see it, right? So now if we have our y equals x, right, you'll notice that this is kind of, it kind of inverses off of it, right? Okay. Oh, I see what's happening. Okay, I was like, yeah, this should look a little bit different. That's because this was placed under the radical sign. That's why this is making a difference. Okay. It was being stingy for a second. Oh well. Okay. Now it looks like it. Now they look like inverses, right? All right, cool. So we have y equals x squared plus 8x plus 16, and then y equals the square root of x minus 4. Y equals the negative square root of x minus 4. And you'll notice that these do look like inverses, right? The way to turn it into an inverse would be to eliminate like half of this, right? So in other words, we could take the positive half in this case. And the reason why this is important to look at is remember that when we had it in the vertex form, it was x plus 4, right? So that actually shifts it 4 to the left, right? So this one, we would have to use negative 4. So we'd have to say x is greater than negative 4. So remember that when you're restricting the domain, the easiest way to do it is kind of graph and look at it. But remember back here, this is vertex form, right? When you have y equals, or x equals y plus 4 squared, right? Essentially what you're doing is you know that this plus 4 means it's moving it to the left, right? So that's why that makes sense. We're going to have to start at negative 4 and go from there. All right, cool. So let's use composite functions to verify that we have inverse functions. So what is the inverse of f of x if f of x equals 2x plus 5? Okay, pretty straightforward linear function. So let's find the inverse real quick. Okay, so if we find the inverse of this, we're going to have y equals 2x plus 5, which means we have x equals 2y plus 5, right? Now we're going to subtract 5 from both sides and then divide by 2. So we're going to get y equals x over 2 minus 5 over 2, right? So So it's a little bit complicated looking, but I mean, in all honesty, it's just fractions, right? Okay, so 1/2 x minus 5 halves. All right, this is our inverse function here. So how can we verify this? Well, let's say that f of x equals our original function, right? Which we already have. And then let's say g of x equals the inverse. So g of x is going to equal x over 2 minus 5 over 2. Okay, so this is g of x. What we're going to do is we're going to plug in f of g of x, and then we're going to plug in g of f of x, and we should get x as a final answer once everything cancels. Right? And that makes sense because if they're inverses, then everything we did, if you do the inverse of that, then that would show that they are inverse functions. In other words, every time we multiplied, if we divide, right? If you take like 3 times x and then divide it by 3, you multiply and divide it by 3, which means x just equals x, right? We already have kind of done this in the past, but now we're just going to kind of use our composite functions to kind of verify this. So let's start with f of g of x, right? So everywhere that we have an x, we're going to plug in this whole thing, right? So let's do this. So we have, if we're doing f of g of x, we're doing f of x over 2 minus 5 over 2, right? Which equals 2 times, right, x over 2 minus 5 over 2 plus 5, right? All I did was basically I took this entire part of the function for g of x and I plugged it in for the x of the other one, right? All right, so let's go and solve for this. First of all, I'm just going to multiply everything by 2, right? So we'll have 2x over 2 minus 10 over 2, and then all of this plus 5. All right, let's simplify that a little more. First of all, the 2x over 2 is just going to be x, right? So we'll have x minus 5, and then plus 5. And then what's negative 5 plus 5? Well, cancels out. So we're just going to, so this is all going to equal x. So far so good, right? When we do, this was f of g of x, and that equals x, right? So now let's do g of f of x. And we should get x again, right? If they are inverse functions, right, which we know that they are, we did the math already. But if we know that they're inverse functions, we should be able to get this the other way. So let's do g of f of x. So what we're going to do is everywhere we have an x in our g of x function, we're going to plug in 2x plus 5. So let's go do this. So g of x was, so we're going to have, this is going to be the same as g of, right? And then remember f of x was 2x plus 5. So g of 2x plus 5. And now everywhere we had an x for our g of x function, we're going to put 2x plus 5. So let's scroll down a little bit more, give us a little bit more space. All right, so this is going to be g of that, which equals, right, or this turns into x, right, which is this top thing. So this is going to become our 2x plus 5. So 2x plus 5 over 2 minus 5 over 2. Okay, so far so good. So if we have, like, we can also do this as like 1/2, right? We could use this as 1/2 as well, and that would probably help us out a little bit. But let's just go ahead and solve this. So 2x plus 5 over 2 minus 5 over 2 is going to equal, right? Because if these are both the same, this is going to be 2x plus 5 minus 5 over 2, right? Because they have the same denominator, so we can just kind of add them across. So now, so this is going to equal, right? Plus 5 minus 5 cancels out, so this is going to equal 2x over x, or 2x over 2, sorry. Right, because the 5's cancel. So 2x over 2, which is the same as equals x. So in other words, g of f of x also equals x. And because both of these equal x, we can confirm that this is, in fact, an inverse function. Which, like I said, we already knew that from the beginning. Like, we're the ones who said that it was an inverse function, right? But this is our way that we can verify. So this is how we check our work, if you want to look at it that way. All right, now the moment you've been waiting for, a word problem. All right, so an artist is making an ice sculpture of Earth for a display. He created a mold that can hold 4.5 liters of ice. Assuming the sculpture is a sphere, what would the radius of ice sculpture be if he fills the mold completely? So we have a mold, assuming it's a sphere, so we have a mold that looks kind of like this, right? And he's filling it with ice. So he'd probably have to, this would probably have to be cut in half or something. You'd have to fill both sides of it, you know, because you can't just fill a sphere exactly. But either way, that's what we're doing, right? We're finding the volume of the sphere. That's what we're doing. Okay. Now, a couple things to know. First of all, this is the volume of a sphere, if you didn't know, 4/3 pi r cubed, and 1 liter equals approximately 1,000 cubic centimeters. Those are both super important for this because it's asking us to find the volume, right? Or the radius, right? And radius, we don't find radiuses in liters, so we're gonna have to convert it. So I just went ahead and took the liberty of like showing you what this is just ahead of time. All right, this drawing isn't really helping us, so I'm just gonna erase it real quick. But you kind of get the idea, right? We're filling a sphere. So, all right, what would be the radius of the sculpture to fill the mold completely? Well, what we're gonna do is we're gonna have to figure out what the radius is, right? So, in order to find the radius, we're gonna have to solve this equation for r, right? So let's go and do that. So if we solve for r, we would, well, let's just kind of rewrite this. So v equals 4/3 pi r cubed. So if we get rid of, if we try to isolate r, I should say, we're going to multiply by 3/4, and then we're going to, well, divide by pi, essentially, right? So if we're, so this is going to be 3/4 pi, right? So it's essentially going to, and this is times v, right? So this is 3v/4 pi equals r cubed, right? So, oh, yeah, so we have one more step, right? And it's basically just to take the cube root of both sides. So if I take the cube root over here, I also take the cube root over here, and that'll give us r, right? So r equals, let's just write it like this, just because this is probably easier for this problem, and you'll gain this intuition on like how these things will be easier. But we're just going to put this as like 3/4 pi, because these are all numbers, right? 3/4 pi are just numbers, and then this is like times v, right? Because 3 times, it's in the numerator, but this will probably just be easier once we have v, right? Okay, so now we have our new function, right? And what we're trying to solve for is, if we created a mold that can hold 5.4 liters of ice, we know the volume, right? We know the volume is 5.4 liters. And we also know that a liter is 1,000 cubic centimeters, so we know that 4.5 liters is 4,500 cubic centimeters, right? So all we're going to do is take our volume and we're going to substitute that in. So we're going to get r equals the cube root of 3/4 pi times 4,500, right? And if we plug this into our calculator, I went ahead and plugged it into the calculator ahead of time just to make our lives a little bit easier. But this is going to be 10.2 centimeters, right? All right. So that is our radius, right? And that's what it's asking us for. That's it. So it'd be approximately 10 centimeters, right? 10.2. Okay. So we didn't really do anything with inverse functions in that one. We kind of just rearranged a formula and kind of plugged everything back in just to double check. All right. Well, let's go ahead and review real quick. So first of all, what we did is we talked about what inverse relations are and then compared that to inverse variation. And then we talked about inverse functions, right? We talked about inverse variation before, so inverse functions. And then here we found the equations of the inverse of f of x, right? In other words, we swapped x and y and then solved for y. That gives us our inverse function. And then we tried, plugging some stuff in. We talked about how to find a specific domain by restricting our domain, right? We were able to find we were able to find the inverse function by restricting the domain. And then we used composite functions to verify. In other words, if we know that f of g of x equals g of f of x, right? And where f of x is the original function and g of x is the inverse of the function, if f of x, f of g of x and g of f of x both pop out x at the end, then you know that those are in fact inverses. F of x and g of x would be inverses of each other. And then the application was kind of just a fun problem. We rearranged the formula a little bit and yeah, got a little bit more practice with moving cube roots around. So, all right. So that was inverse relation and inverse functions. And that's the end of Unit 5. Congratulations. Now off to Unit 6, where we're going to talk about logarithms. I'll see you then.